All right, welcome back, folks. Let's go ahead and jump into Chapter 10 here. Chapter 10 is called Comparing Two Populations or Groups. And amazingly, that's exactly what we're going to be doing. We're going to be looking at inference procedures between two populations or groups. And we're going to start by comparing two proportions. And I know that right now, if I asked every one of my students what type of variable we're talking about, if we're looking at proportions, you would say categorical. Okay, so let's go ahead and jump into the notes from here. You might be a little intimidated by the notes packet for chapter section 10.1. It is a full 6 pages long, but I promise you it's not that bad. The first 2 pages are all theory and formulas, and then the rest of it is examples. Should go pretty quickly once we get through the theory stuff. Okay, so where does chapter 10 fit? This is our the third of 5 chapters on inference. We've already done confidence intervals in chapter 8. We've done significance tests in chapters 9. And then what happens here in chapter 10 is we do both confidence intervals and significance tests for a difference in proportions and a difference in means. And we're going to use these when comparing 2 independent random samples or 2 groups in a randomized experiment. Just as an FYI, questions about Chapter 10, pretty popular on the AP exam, so make sure you just keep that in the back of your mind as you work through this chapter. All right, so here's the situation. We got 2 different populations or treatments, and the parameters that measure population 1 and population 2 are P1 and P2 respectively. The statistic that measures a sample from each of those populations is P1 hat and P2 hat respectively, of course with sample size N1 and N2 respectively. And just a few comments here about how we're going to be comparing populations. We compare populations or treatments by doing inference about P1 minus P2. And remember, inference is when we want to learn some things about a population based on sample. And this P1 minus P2, we're looking at change here, or gain. Might even call it delta if we get really mathy. Okay, the statistic that measures this is P1 hat minus P2 hat. And to use P1 hat minus P2 hat for inference, we must know the sampling distribution for P1 hat minus P2 hat. So the rest of this page, we're going to be talking about the sampling distribution for P1 hat minus P2 hat. I would encourage you, if you don't remember what a sampling distribution is, go back and review chapter 7, please, because chapter 7 started our discussion about sampling distributions, but we've been using it in every chapter since then, the properties of sampling distributions. Okay, so let's now talk about that sampling distribution of P1 hat minus P2 hat. So let's say we choose an SRS from population 1, and that size is N1, and the proportion of successes in that sample is P1, and then we do the same thing with the second population, so we have N2 and P2. The sampling distribution of P1 hat minus P2 hat is approximately normal if all of these quantities right here are at least 10. The center of the sampling distribution of P1 hat minus P2 hat is that value right there. And why is that? Because P1 hat and P2 hat are unbiased estimators of P1 and P2. The spread, we'll use standard deviation to measure the spread of the sampling distribution of P1 hat minus P2 hat. And oh boy, does this formula look intimidating. Basically, we have a whole bunch of stuff underneath the square root symbol here. We'll come back in a few minutes and talk about that. And that formula is good as long as each sample is no more than 10% of the associated population. Okay, I hope that each of these things, each of these features, shape, center, and spread, remind you of conditions from previous chapters. I hope this first one reminds you of the large counts condition. And I hope this second one reminds you of the random sample or random assignment of treatments. Last but not least, this standard deviation formula down here, this should remind us of the 10% condition when we're sampling without replacement. Okay, so now let's go down to a bonus question here. We're going to go back and kind of analyze this formula in a little more detail. Okay, although we will work with specific values of P1 hat and P2 hat, they're both random variables. And I hope you remember that we spent an entire chapter talking about random variables. If you don't remember, that was Chapter 6. Okay, so both P1 hat and P2 hat are random variables that could vary in repeated samples of size N1 and N2 respectively. So let's go back and look at the formula for the standard deviation of the sampling distribution P1 hat minus P2 hat. And where does it come from? Well, it looks like two things are added. It looks like what we've done here is added this quantity and this quantity and then taken its square root. Okay, this should remind you of something back from the random variable chapter, and that is the following. When combining independent random variables, variance adds, standard deviation does not. So even though the sampling distribution is P1 hat minus P2 hat, even though our combination here is subtraction, we are adding variance, and then by taking the square root, after we add those two quantities, we end up with standard deviation. All right, folks, I'm going to shut down the video here and then pick it back up in part 2.